Sam and I are going to be presenting our CalcuLatency system today. So global events affect the internet in new ways every day. Users face security and privacy threats from various entities that seek to disrupt, tamper with, and monitor their internet traffic. As a result, we are increasingly seeing users turn towards privacy-enhancing tools such as VPNs as a panacea to overcome various security and privacy issues, thereby fueling the growth of the commercial VPN ecosystem into a multi-billion-dollar industry. However, as VPNs grow in popularity, we also have to note that there is another side to their use. While they were initially intended as a privacy-enhancing tool, some bad actors are also misusing VPNs to hide their identity while carrying out attacks or other nefarious activities against service providers. These service providers also have a variety of reasons to impose restrictions on the usage of their services, for instance, including media licensing restrictions, geographic limitations, e-commerce needs, apart from the security reasons. So server-side operators have a need to identify and stop threat actors and bad faith users from using proxies to misuse their services. To combat such misuse of proxies, many companies use black box solutions to identify VPN or proxy use, or they may resort to collecting more data about their users. For instance, like comparing their current IP address with the previous list of IP addresses they've seen from the user, or just more simply keeping an extensive profile on their users. So in short, balancing abuse prevention techniques with a privacy-focused approach is a hard task. Our aim with this work is to answer the following question. Can service providers build a system using minimum connection features, such as latency, to infer VPN or proxy use without jeopardizing user privacy or having the need for data collection? We found that indeed we can leverage network latencies at different layers to identify proxy connections from non-proxy connections. So let's take an example. Say user 1 from Thailand is connecting to the service provider in California, but is using a VPN server in New York. And let's say their neighbor user 2 is connecting to the same service in California, but without a VPN. So here, if the server-side operator records the application layer RTT for both clients, say using WebSocket measurements or WebRTC, that measurement is going to be end-to-end. So in both cases, it's going to be originating from the web server, let's say an echo measurement that will be sent to the web browser of the user and then back to the server. Now, apart from this, the service provider can also send out network layer measurements towards the public IP that they see contacting them. So in this case, user 1's public IP would be their VPN server IP, but in user 2's case, that would be the public IP that's their router IP or their NAT, which are both going to be very close to them. So here, the network layer RTT would be small for user 1 and would be a larger one for user 2. So from this example, we can see that since user 1 is using a VPN, the RTT difference between the application layer and the network layer would be large and would be noticeably larger than for user 2, who is just connecting to the service directly. So this difference is what our system aims to measure and use to differentiate proxy use. But before we get into how we built the system, let's set up some assumptions under which the system operates. We require that the user and the server have an application layer connection. And our system aims to detect long-distance remote proxy use, that is when the user uses a server that's much farther from them. And we also assume that our client does not control the network behavior of the proxy and does not selectively delay certain packets. Now, these are reasonable assumptions to make for users who use commercial VPNs or their own proxy servers to commit some sort of coordinated abuse. So in this system, CalcuLatency, the main idea is to devise different measurement methods for different layers. For the application layer, we use WebSocket measurements, which can run from the browser, say by using making the user interact with the CAPTCHA. And we could also use other application layer protocols instead of this, like WebRTC. On the network layer, however, the measurements have to be initiated from the server side. So in order to maximize success, we draw on 3 separate techniques to estimate the RTT. So first, on the transport layer, we use the incoming TCP handshake from the user. And on the network layer, the server sends out ICMP pings towards the client's public IP. And we also run a modified trace route to infer the RTT difference. Now, the other methods are fairly standard. So I want to talk about or highlight the modified trace route method that we implemented. So as a background, traceroute is a network diagnostic tool that leverages the fact that network hops or network hops or routers edit the IP header of a packet and reduce the time to live field as they process and forward the packet. So you can send out packets with incrementing TTL to be able to determine the path. However, a key challenge is that it's not always possible to reliably get the remote IP address network stack to respond to unsolicited packets. So we found an old security forum post from 2007 that mentioned the method zero trace. So we took inspiration from this idea and we re-implemented it in Golang. So we use the existing TCP connection that the client initiates towards the server and use that connection to send trace packets with incrementing TTL that match the 5 tuple of the connection. So these packets can therefore pass through stateful firewalls and traverse NATs, and you can find more about this implementation from our GitHub repository. So putting together all of these measurement methods, we created a system called CalcuLatency. We send WebSocket packets to determine RTT on the application layer, and we use the TCP handshake, ICMP ping RTT, and zero trace on the network layer. So now Sam will go over our evaluation and our results.
Thank you very much, Reethika. So we conducted 2 different sets of evaluations. The first was a study of each of the building blocks of our measurements in isolation in order to judge their reliability. We then evaluated the entire CalcuLatency system as a whole, putting together the 4 different RTT measurement sources that Reethika just explained. We used a 2-pronged approach for evaluating the system in its entirety, and I'll talk about this in the next couple slides. So, the first approach was a controlled testbed experiment using devices in different networks on 4 popular browsers. We automated the testing mechanism and ran direct measurements from 4 different countries in 12 different networks. We used geo-distributed servers as proxies from 10 different VPN providers and collected a total of 891 experiments. The next part of our approach was a public crowdsourced evaluation. We did this by hosting a fully functional web server on a university subdomain. We recruited users on Twitter to run measurements using a VPN and without one, and collected data for 15 days. With this public evaluation, our aim was to diversify the types of networks and devices that we tested. Overall, we were able to collect 283 experiments from users in 37 countries from all 6 continents, with VPN servers from 51 unique autonomous systems and direct measurements from 93 unique autonomous systems. So, what did we learn from this evaluation? We were able to determine a threshold RTT of 50 milliseconds that can separate direct client-server connections from those that use remote long-distance proxies. And this works with considerable accuracy. The empirical threshold represents the RTT difference between the application layer latency and the network layer latency. So from our controlled testbed evaluation, we saw that in over 98% of direct measurements, the RTT difference is less than our threshold of 50 milliseconds. Whereas in almost 90% of the VPN measurements, the RTT difference is well over the 50 millisecond threshold. So we then investigated the false negative measurements where the user used a VPN, but the RTT difference was less than that 50 milliseconds. We found that in 61% of those cases, the VPN was located very close to the user. This is out of scope for us, as our aim is to identify long distance and remote proxy use. So looking at the remaining 39% of the false negative cases, we found that all of them mapped to 14 unique VPN IPs. And we looked at these more carefully. We found that these VPNs were supposedly located in Central or South American countries. However, based on the ICMP RTTs that we actually measured, it proved that even based on a liberal estimate of a speed of internet calculations, that these advertised locations are actually not possible. And these are potentially virtual VPN servers whose true geolocation is actually much closer than what is reported by the VPN providers. Next, we're going over the public crowdsourced measurements. We found that in 98.8% of the direct measurements, the difference in RTT is less than the 50 millisecond threshold, and in approximately 64% of the VPN measurements, the RTT difference was over the 50 milliseconds. So we looked into the false negatives in this experiment and found that in 77% of those cases, the VPN was again located very close to the user, similar to the results of our testbed experiment. So looking at the remaining 9 experiments, some of them failed either the zero trace measurement or the ICMP ping. And for these cases, we would label them best effort. In a real world implementation, they would be marked for a remeasurement. So in short, through our study, we were able to show that network latency can indeed be leveraged as a first step in identifying clients that connect to a particular service provider through a remote long-distance proxy, without the need to collect extensive data from the user. However, it is important to note that not all VPN traffic is abusive. Given the specific use case that we designed the system for, the limitation of only detecting remote and long-distance proxies can actually become an advantage, as it is very difficult to misuse this technique to employ a blanket ban on all VPN servers for people who are simply trying to use VPNs to enhance their privacy and security. These users can use nearby, faster servers for these purposes. And with that, we would conclude and open the floor for questions. Thank you.